Hello, Matthew. I'll be right back. I'm going to fill up my water.
Hi.
Hey, Matthew, how's it going?
I'm well.
Ashworth, how are you doing?
Good.
So do you guys remember the definition of a group?
Yeah, it had the 4 traits. It had to be what, commutative?
Nope. Commutativity is not
It
necessary.
was associativity, right? Uh, uh, wait,
Okay,
damn, I
so
can't remember.
the if you're ever thinking to yourself, I can't remember the definition of a group, look at the some simple examples of a group. The simplest possible example of a group is the integers under addition. So the integers under addition, let's see if this will load.
One was closure. Yeah, I remember that.
Closure, that's kind of the most basic one. Then we have identity. So that means we have to have some element where when we apply it, nothing happens. We have to have associativity. So associativity is nice. We already said that. And then we need to have cancellation or inverses. So here's an interesting theorem, which I'm going to leave it to you to prove. Just, if you're idle. So let's write theorem. Only assuming the 4 properties prove that the identity, I guess I'll prove this, but I want to give you a second to try to think of it. You only allowed to use those 4 rules. The identity element of a group is unique. How would we even prove something like that, especially only using the 4 properties?
By unique, do you mean like for each specific group, it has a different identity?
I mean that if in a group you have 2 elements where when you apply them, nothing happens, those in fact are the same element. So there's only one.
Okay.
So let's write this equation. For contradiction, we're going to assume that so in a group, typically we write E as the identity if it's not something that is like the integers. There's a lot of things that could be the identity. Or maybe I'll write I. I is better. So we have I. A is one of them. And let's say we multiply that by some element X. And we're saying that we have another element IB, which is also an identity element. So you can actually do this in one line using the rules of a group, using the traits of a group. Well, X inverse exists, right?
Yeah.
So just multiply both sides on the left or on the right by x inverse. So whatever that is the identity of the group, or a identity of the group. In this case, we're not assuming that they're unique. But it turns out that the identity times anything else is just that anything else. Therefore, there's only one identity in every single group. If you have multiple identities, then it's not a group. So you're missing a property. That's one way of checking it. All right, so let's actually look at a group that's not commutative. Well, I actually gave an example of a group that is not commutative already. So let's look at our examples again. We had the integers under addition, that's clearly commutative. We had the integers mod n under addition, that's commutative. We had the non-zero rational numbers under multiplication, that was commutative. We had the integers whose GCD with a number is 1 under multiplication, that is commutative. Okay, let's see. Then we had the proof right here, isometries. Why is the isometries group of a space non-commutative?
If you translate something, then reflect it, it's different than reflection than translating.
Good. The problem here is the reflection. If I removed translations from the group, it would still be a group, but doing a reflection and then a rotation is the opposite of doing that rotation and then that reflection. So yeah, the reflections are the problems. And so let's look at another non-commutative group, which actually turns out to be the exact same group. Non-commutative isometries is an example. So I'll put example 1, but example 2 is 2 by 2 matrices A, B, C, D, where A, D minus BC is equal to plus or minus 1. And it's a theorem that these are actually the same group. But let's pretend we don't know that. And this is under matrix multiplication, which is the same as function composition. That's why I'm writing an open dot. So let's prove it. Do you guys know how to matrix multiply? I'm going to take the silence as a no. So let's talk about how to multiply matrices and then explain why it makes a group E, F, G, H. Okay, and does anyone recognize this AD minus BC?
It's a determinant.
That's a determinant, yep. Something very geometrical about why those two groups are actually the same. So when you multiply a matrix, the new matrix, if this is pretend an m by n matrix, and this is an n by q matrix, then this becomes an m by q matrix. So in this case, these are 2 by 2 matrices. So a 2 by 2 matrix times another 2 by 2 matrix gives us a 2 by 2 matrix. Therefore, it's at least closed. So we should write that proof that it's a group. 1, it's closed, or that's the zeroth property actually. Check. Okay, so when you multiply a matrix, you're gonna multiply the rows by the columns in a special way. So it's actually gonna be row 1 dot column 1. And then, so that's the first spot. Oh, that's the wrong thing to erase. So this is the 1, 1 spot right here. in the 1, 2 spot, we're going to have row 1 dot column 2 of this one. In the 2, 1 spot, can you guess what we're going to have here?
Row 2, column 1.
Yep.
Wait, by row 1 and row 2, do you mean like the sum of the numbers in that row?
Yeah, so in the first matrix, we're only carried, so the dot product of, let's say, R1 comma R2, that's bad. I already just used those variables. So let's say X1 comma Y1 is our first row, and then dot our column X2, Y2. I'm just writing it this way to be suggestive. That's X1, X2 plus Y1, Y2. So this is actually the same dot product that we've been using in geometry, which is another reason why these two groups are the same. So we have the 2, 2 spot here. This is going to be row 2 dot column 2. And then, so we have closure. In this case, we're going to need an identity. And I'm going to claim that it's this matrix. And then we're going to prove that that's actually the identity. So if we take A, B, C, D, matrix multiply that by 1, 0, 0, 1. Also, I guess, so actually, let me finish this thought over here. This is actually not a commutative set. We don't know if it's a group yet, but it's not commutative for sure, because in general, if we have A, B, C, D times E, F, G, H, and we matrix multiply them. So that's going to be A times E plus B times G. So row 1 dot column 1 for the first entry. And then we're going to have row 1 dot column 2 for the second entry. So that's going to be AF plus BH. And then for the first entry in the second row, we're going to have BC plus DG. Sorry, CE plus DG. I make mistakes doing matrix multiplication all the time. I always have to check it. And then finally, the last entry is going to be CF plus DH. And so if we do it in the other direction, GH, A, B, C, D. Someone tell me what goes in the first row, first column.
EA plus FC.
Yep. Okay, and Asherth, what goes in the first row, second column?
EB plus FD.
That's correct. And so we can already tell that these things aren't going to be the same, just for arbitrary numbers. I'm just going to finish writing this out for the completeness of my notes. And then we're going to have BG plus DH. Okay, so this is an example of a non-commutative set. So let's return back to the proof that this is actually the identity. This is going to be A times 1 plus B times 0. So that's just A. A times 0 plus B times 1. That's just B. C times 1 plus D times 0. That's just C. C times 0 plus D times 1. That's just D. Okay, so we get what we need. And then I'm pretty sure in group theory, we take it as an axiom that the identity needs to be a two-sided identity, meaning that if you multiply on either side, you get the same thing. But here we're trying to confirm that something is a group, so we actually have to check both sides, especially since we've confirmed that this is a non-commutative setting. So we have 1, 0 dot AC, so that's just A. And then we have 1 times B plus 0 times D is B, and then 0 times A plus 1 times C is C, and 0 times B plus 1 times D is D. So yes, this is a two-sided identity. So then for 2, associativity, you could do for matrices, we typically denote matrices with capital letters. You could just check that ABC is equal to ABC manually. We're not going to do that manually. We're just going to say that function composition is associative. And it might not sound like this is a good proof. You know, it seems like I haven't actually demonstrated something, but that's because I haven't really defined matrices correctly here. So far, I just said, oh, it's a table that we're multiplying in a certain way. But if you take an abstract linear algebra class, then you will understand why this is an actually okay proof. And so then the final one we have to prove is inverses. So I'm just gonna give you the definition of a matrix inverse. So that's A, B, C, D inverse is equal to 1 over AD minus BC times the matrix. You're going to flip the elements on the main diagonal. So that's going to be D, A. And then you're going to take the elements on the off diagonal and make them negative. Now, one thing to be aware of is this formula only works for 2 by 2 matrices. So I guess we should just check that this actually gives us the right answer. So 1 over AD minus BC. And when we have a number on the outside of a matrix, it just means that we could factor it out from all the entries. And if we wanted to put it on the inside of the matrix, we would just multiply each entry by that. So I'm going to keep it on the outside for brevity for now. So D minus B minus C comma A. That's going to be A, B, C, D. And so if we matrix multiply this, we're going to get 1 over AD minus BC times the matrix. That's going to be A times D minus B times C. So we get AD minus BC here. And then we have D times B minus B times D. So that's a 0. And then we're going to have minus C times A plus A times C. So that's another 0. And then minus C times B plus A times D. That's going to be AD minus BC. So this gets us back to our identity matrix. So matrix multiplication is super cool, does a lot of nice things. And already we're kind of seeing why this might be relevant for our thing to be a group. AD minus BC equals plus or minus 1. We have to divide by this. So I actually haven't proved closed just yet. I should have put a part 1 right here. Let's put a part 1. Come on, give me the marker. What are you doing? Give me the marker. Part 1. If this was just not equal to 0, well, I guess we still haven't shown that. What we need to show is that this quantity, the determinant of the matrix, is the same as it is still plus or minus 1 if the original 2 were plus or minus 1. Right, so what we need to show is that det of A times B equals plus or minus 1 if det of A and det of B equals plus or minus 1, right? So there are a lot of really intelligent proofs of this fact, but I'm just going to do the grunty proof. So we have AD minus BC equals plus or minus 1. And then the other one we said EF GH. So that's going to be EH minus FG equals plus or minus 1. So these are our hypotheses. And then we need to find the determinant of, we have AE plus BG. And then comma AF plus BH. And then that was CE plus DG. Come on. Active inspire. And then the final one was CF plus DH. Okay, so if we take the determinant of this thing, then we get AE plus BG times CF plus DH minus CE plus DG times AF plus BH. So let's multiply this out. So we get AECF plus AEDH plus BGCF plus BGDH, and then minus, in parentheses, CEAF plus CEBH plus DGAF plus DGBH. Okay, and we are going to want some cancellation to occur. Specifically, this CEAF cancels with this AECF. And this, let's see, what else? Should be two more terms canceling.
Last terms.
The last term.
The last
Yeah.
terms. Great. Great. So then we get AEDH plus BGCF minus CEBH plus DGAF. Now I'm going to put everything with an AD in it next to each other. So we have ADEH plus ADGF. And then, oh, sorry. There should be a minus sign right here. And then we have everything else is going to be,
The CBs.
yep. BCEH. So tell me the punchline. What's happening here?
Once you factor, you get things that look like determinants.
It specifically looks like the product of the original
Yes.
two. Yeah, so we should have a sign difference here.
Yeah, you just didn't write a
Yep.
BCGF. Like you should have been minus BCGF, right?
Yeah, so we get
No, never mind.
ADEH minus GF. You guys already saw the pattern. I'm just writing it for the completeness of my notes. EH minus GF. And so then we can pull this AD minus BC equals EH minus GF, which is equal to the determinant we started with. So it's equal to plus or minus 1 times plus or minus 1. In general, if we have two matrices, A and M, the determinant of A and B, the determinant of A times B is equal to the determinant of A times the determinant of B. This is one of my favorite facts. So I claimed before that actually this group of 2x2 matrices whose determinants are plus or minus 1 is actually the exact same group of isometries of the plane. I should have specified that it's isometries of the plane where we have removed translations, because a matrix multiplication leaves the origin in place. So I should put minus translations. So it's not something I will prove, but I will just state that a reflection is the same as a 2x2 matrix with determinant minus 1, and a rotation is a 2x2 matrix with determinant equal to plus 1. Okay, let's look at another matrix group where all the determinants are plus 1, but that doesn't really matter to us. And then I'm going to compare that to, yet again, another matrix group, or a completely different group. So I'm going to leave this one actually a couple tasks up to both of you. So we have this one and this one, and we have this one, and we have this one. actually, well, so we need to prove that this is a group. We already have the identity matrix in here, and we already know that matrix multiplication is associative. So now we need to confirm that, oh, whoa, this last one is messed up, sorry. Now we need to confirm that we have inverses and that it's closed. So in order to do that, let's just literally make a multiplication table. So then 1, 0, 0, 1. And it turns out that this group is actually a very familiar group to you, even if you have never thought of this group in terms of being a group. But I guarantee you have thought of this group many hundreds of times. So if someone can tell me what these matrices are just convoluted labels for, I will be very impressed, but that's the punchline basically of this, and we'll figure it out soon. So the identity times the identity, that's obviously the identity for all of these. So I'm just not going to write these because it's obvious what the identity times anything is. So tell me what this entry is on this diagonal now. So what's minus 1, 0, 0, minus 1 squared? And let's say that this is our first column and this is our second. So we're doing this times this.
Is it 1001?
Yep. So this thing is its own inverse. And let's do this times, so minus 1, 0, 0, minus 1 times 0, 1, minus 1, 0. Can someone tell me what that is?
Oh, wait, which ones?
This one and this one. There's actually a really cheap move that you can do. So notice that minus 1, 0, 0, minus 1 is equal to minus 1 times 1, 0, 0, 1, which is the identity. So minus 1, 0, 0, minus 1 is actually just, when you multiply that by any of our other matrices, all it does is multiply their contents by -1. So what we get right here.
Yeah, I multiplied it out. It's the last one. That's the 0, -1 one.
Yeah. So that's the intelligent thing that you're supposed to notice, is that this is actually almost the identity matrix. It just multiplies everything by -1. It represents a 180-degree rotation, by the way. So then if we do the same thing here, this times this, well, that's just going to multiply it by -1. So that's going to be 0, minus 1, 1, 0. And then it, again, this times this is just going to multiply it by -1. So 0, 1, minus 1, 0. And so now what is this matrix here times this matrix here?
Is it the second one? The 0, -1, 0.
Mm-hmm. And so what is this matrix here times the fourth one? The third matrix times the fourth matrix.
The first one?
It's not the first one. Oh yeah, it is the first one. It is. My apologies. Yep, it is the first one. All right, and let's do it in the opposite order now. So what's the fourth matrix times the third matrix?
The same thing.
Yeah.
Same.
So we said that matrix multiplication generally doesn't commute, but it doesn't matter what this thing is. We've actually gotten a symmetric table, symmetric multiplication table. But can someone tell me what the last product is?
The second one.
It's the second one. Okay, and I'm gonna write these final ones here so that I can do a relabeling of these matrices, and we can see that this is actually a very familiar group. -1, 0, 0, -1. And then we have 0, 1, -1, 0. And then we have 0, -1, 1, 0. Someone want to try to guess what this group is? What does this multiplication behave like? What set of 4 things multiplies like this? Also, even though matrices don't commute in general, we have found a set of 4 matrices that do commute, which is pretty interesting. Well, one thing I'll say is that all 4 of these matrices have a determinant of 1. So that tells you that we should think of them as rotations. So if I say our first matrix, the identity matrix, let's just call that 1. And then our second matrix, well, we should call that -1. And then if I call 0, 1, -1, 0, if you notice, this thing actually squares to -1. So let's call that I. And then this thing, which is its negative, -1, 0, 1, 0, also squares to -1. So we should call that -I. And so clearly the set 1, -1, I, and -I is a group under multiplication, right? Because we have inverses, we have associativity, we have the identity element, we have closure. These are actually the same group. These matrices are very special. And should I find a group that doesn't commute? Maybe I'll stop. Matrix groups, there's so many matrix groups. I could talk about them forever and ever and ever. So let's see, how much time do I have left? Only 20 minutes. Okay. I thought that by talking about matrices, I could prepare for the next thing, but let's get to the good stuff. So last time I left you with, oh, dang. All right, so let's return back to another geometric group that we were talking about. The circle. And I'm going to choose the point 1, 0 to be our identity element. And then also using some techniques from last week, we can find a parameterization of this circle like this. And then we can notice that our group multiplication, or group addition, sorry, in this case, you can call it group operation, group multiplication, group addition, however you would like. If we choose this point to be our identity, then all we need to know is the slope between these 2 points in order to calculate their sum. If we just plug it back into our Diophantus's method of secant parameterization of the circle. So the slope between this is going to be xb minus xa over yb minus ya. And so if we plug that into here, then we get xb minus xa over yb minus ya squared minus 1 over 1 plus the same thing. And then we're going to have 2 times this. For 1 plus this. It's going to be xb minus xa over yb minus ya squared. And So let's clear denominators of this. So we're gonna get xb minus xa squared minus yb minus ya squared, comma, let's rewrite this as xb minus xa squared plus yb minus ya squared, comma, that's going to be, if I multiply this by y minus a, yb minus ya squared, that's going to be 2 xb minus xa divided by yb minus y. What's the same denominator? Let's keep it consistent. xb minus xa squared plus yb minus ya squared. And we're going to get some nice cancellation if we expand this out. So that's going to be xb squared minus 2 xa xb, and then coming from this thing over here, we're going to have plus ya yb, and then we're going to have a plus xa squared, and then a minus, oh no, so sorry, this should be a minus sign here. Then we have a minus, maybe I should put these close together. Yeah, let's do that. Let's do that. Let's rearrange the order of this. So it's going to be xb squared plus xa squared minus yb squared minus ya squared minus 2xa xb minus ya yb. What's going wrong here? At some point, we're going to want to use that xa squared plus ya squared is equal to 1. And I also wrote this one right here incorrectly. Let's see. I feel like I'm burning up our time. Come on. I stopped using Active Inspire so that this would be easier. Oh, now it's just not working at all. Oh, okay, just had to think about it. All right. So yb minus ya. Okay. Did I plug in the wrong slope? I did plug in the reciprocal of the slope. How did that happen? Okay. So that's kind of embarrassing. All of these should be their reciprocals. So that only affects us right here. The signs should be reversed, but that's actually not that big of a problem. Please, please give me the eraser. Okay. What we want to get is this. We want to get xayb plus xbya, comma xaxb minus yayb. And then we can prove something about angle addition. Oh, we never even proved those identities. The ones that I gave for homework. I never explained where they came from. Looks like we're not even gonna have enough time to prove Pascal's hexagram of mysticum. Okay. We need to get something that simplifies down to that. So come on, please, just give me the eraser. I don't know what its issue is. Here, let's just erase all of this, and I'm going to give them easier names to write down. Okay, so let's say that, first of all, I'm going to set t equal to m over n, just to show something neat that comes from this as well, and it'll make our lives easier down the road. So if we set that to equal to m over n, we get m over n squared minus 1 over 1 plus m over n squared, comma 2m over n over 1 plus m over n squared. And then so we get m squared minus n squared plus, comma. If we multiply the top and bottom of this by n squared over n squared, we get n squared plus m squared. So I'm just going to rewrite it this way, comma 2mn over m squared plus n squared. And this gives us a famous identity, m squared minus n squared squared plus 2mn squared equals m squared plus n squared squared. And so if we set m equal to, let's say point A is equal to little a comma b, and point B is equal to little c comma d. Then if we set m equal to b minus d and n equal to c minus a, then we end up with b minus d squared minus c minus a squared over b minus d squared plus c minus a squared. So here we have a squared plus b squared is equal to 1, and c squared plus d squared is equal to 1. And then we have 2b minus d c minus a over, let's say, b minus d squared plus c minus a squared. So we might have to be clever here if we're going to factor this correctly. What we want to show, just so to give you guys something to try to work out while I struggle and deal with the consequences of not having written this portion of my notes beforehand. We want to show that this is equal to AD plus BC, comma, AC minus BD. Do I have that backwards? Yes, I do have that backwards. We want it to be AC minus BD, comma, AD plus BC. So if we rewrite this, we get b squared plus d squared minus c squared minus a squared plus 2 times bd minus ca. And this is still backwards. Is it? Did I do something stupid like flip the slopes again?
Just at the top. Oh, sorry, at the bottom. At the bottom. So yeah, it would be plus CA.
AC. And it should be minus BD.
No, the two BD minus CA. It should be a plus CA, like all the way down.
Why a plus CA all the way down?
No, scroll down. In the B squared plus D squared minus C squared minus A squared,
Uh-huh.
it would be minus 2AC. So it would be minus 2AC.
Ah, there we go. So that's going to be AC minus BD. There we go. And then here we're going to have B squared plus D squared minus C squared minus A squared plus 2AC minus BD.
Wait, doesn't the thing you wrote down produce like the same result?
Yeah, sorry. Should
If
be
you just
minus
you're
signs.
talking about the first exponent, right? Like the B squared, B minus D squared minus C minus A squared. You're talking
Yeah,
about that,
yeah.
right? Just simplifying it, minus 2 BD minus 2 CA. So you're if you wrote plus 2 AC minus BD.
Minus BD. Oh, so yeah, it should be flipped. BD minus AC. We have a squared minus b squared over a squared plus b squared. We can add to a b. No, we don't want to do that. Maybe I should use different variables. I think we might have to complete the square in an intelligent way. Squared minus y squared. X squared plus y squared. Shucks, I should have done this part beforehand. Well, it's also kind of nonsensical to do this part and conclude anything meaningful without proving the two identities that I did before. So let's spend the remaining of our 14 minutes proving that this group actually is the same as the angle group, at least in the circular case, because I want to use the method of secants to conclude the angle sum formulas or give alternate proofs of them. You have to know that they're the same group, and we're actually going to have to use the angle sum formulas to get that they're the same group to begin with. But, you know, so come on, please don't do this to me. Just let me write. Okay. All right. So we can take 2 points on the circle and parameterize them by an angle, theta and phi. So this is cosine theta, sine theta, and cosine phi, sine phi. And so the slope of the line between them is going to be here, let me look at the identities that I sent. There's a couple different strategies that we could use, and I don't want to waste our times. Okay, so yeah, we have the slope. Okay. And we claim that if we translate this line here, ooh, come on, close enough, that this point should be cosine theta plus cosine phi sine theta plus sine phi. And so let's use this formula for a line. Y minus 0 over x minus 1 is going to be equal to, that's going to be sine theta minus sine phi over cosine theta minus cosine phi. And so if we rearrange this, we get cosine theta minus cosine phi equals times y equals sine theta minus sine phi times x minus 1. And I guess I'm going to rewrite this by moving everything over to the other side. So we have sine phi minus sine theta times x minus 1 plus y cosine theta minus cosine phi is equal to 0. And so these two groups are going to be the same group if and only if, when we substitute this point in for x and y, we actually do get 0. That is equivalent to this point lying on this line. So let's do just that. So we're going to have sine phi minus sine theta times, and I'm going to, no, I wrote this point wrong. Oh, it won't let me erase. Why can't I just select the eraser? What is wrong with this program? There we go. That's going to be cosine theta plus phi, comma sine theta plus phi. Okay, so I'm going to expand those out. So cosine theta plus phi is cosine theta cosine phi minus sine theta sine phi minus 1 plus, and then our y value is going to be cosine theta sine phi plus cosine phi sine theta times cosine theta minus cosine phi. And we need to see what this is equal to. So if we distribute, we get cosine theta cosine phi sine phi minus sine theta sine squared phi plus that's going to be cosine theta cosine phi. Let's say cosine theta sine theta cosine phi, and then plus sine squared theta sine phi. And then we distribute this one, we're going to get, oh, and then we have a minus 1. So that's going to be minus sine phi plus sine theta. And then here we're going to get plus cosine squared theta sine phi minus cosine theta cosine phi sine phi plus cosine theta cosine phi sine theta. Feels like there was a mistake that happened. And then we have minus cosine squared phi sine theta. There was a mistake. So we're gonna have, let's just circle what cancels out. So this is going to become, oh, it's not a mistake. Beautiful. That's going to become minus sine theta. And then if we circle this, the other one is right here. It's going to become plus sine phi. And then this cosine theta, cosine phi, sine phi is going to be this. And finally, this cosine theta, sine theta, cosine phi, and this minus cosine theta, cosine phi, sine theta is going to cancel out as well. So we just have what's left over minus sine theta plus sine, minus sine phi plus sine theta, which is equal to 0. So that point actually does lie on the line, which establishes the equalness of these groups. They're secretly the same group. I haven't really made it clear how you rigorously say when two groups are the same. And I only have a few minutes, but let's do the same exercise for the hyperbola. So let's call these 2 points cosh theta sinh theta and cosh phi sinh phi. And then if we take, oh, maybe these were bad example points. Ooh, let's try again. Let's make this a parabola where we zoomed farther out. But so I want you to recall the problem with hyperbolic cosine is that it's even. So we're not actually establishing an equivalence of groups in this case. What we're establishing is an equivalence of a group to a subgroup of another group. I haven't defined what a subgroup is, but based on the name, you should be able to figure it out. And this is cosh phi sinh phi. And the sum of their angles is going to be somewhere up here. So I'm going to call that cosh theta plus phi sinh theta plus phi. And so we have the line between them. The equation is going to simplify to sinh theta minus sinh phi times x minus 1 plus cosh phi minus cosh theta times y is equal to 0. And so let's substitute in our angle sum formulas here and see if we actually get an equality. And that will establish that the points on the unit hyperbola that can be parameterized by an angle form a subgroup of the point addition group. So next time, I guess I will prove Pascal's theorem to the best of my ability. The problem is you guys don't know linear algebra is really the big deal breaker for that proof. I'll see if I can. I was really happy that I was able to prove Taylor series without too much advanced knowledge. There's actually a way better proof of Taylor series that I would like to give, but it's not that it's unrelated to what we're doing. It's just it's very far away from what we're doing relative to the types of problems we solve. We've already gone very far away, but the story with angles is actually way more interesting than what you get, just in your daily life at high school. There's way more going on there. And this is going to be cosh theta sinh phi plus cosh phi sinh theta. So let's multiply all of this. So we get cosh theta cosh phi sinh theta plus that's going to be sinh squared theta sinh phi minus sinh theta just want to make sure that nothing stupid has happened yet. So then we have minus cosh theta cosh phi sinh phi minus sinh theta sinh squared phi. Oh, okay, yeah, nothing stupid has happened. All right, sinh squared phi, and then plus sinh phi, and then we have plus cosh theta cosh phi sinh phi plus cosh squared phi sinh theta. And then I'm going to scroll down just a little bit, minus cosh squared theta sinh phi and minus cosh theta cosh phi sinh theta. Okay, all right. So this right here is automatically going to cancel with this right here. And then we have, that's actually a false thing, which I just said. It's going to cancel with the one above it. But this one is going to cancel with this one. It has a minus sign. And if we combine the sinh squared theta with sinh squared theta, sinh theta? No, that should be a sinh phi, pretty sure. That is a sinh phi, okay. Oh, oh no. Why is it doing like every 5 minutes? We've wasted so much class time being frustrated at this. All right. So that is going to combine with this. So we have a sinh squared theta minus cosh squared phi. That becomes a -1. So we have minus sinh theta. And then this right here is going to cancel, or is going to combine with this thing. They both have a sinh theta on them. We have cosh squared phi minus sinh squared phi. That is a +1. So we end up with a plus sinh theta. And then what's left over is a minus sinh theta and a, that's not a sign, that's a sinh. And a plus sinh phi. And that all cancels to 0. So the points on a hyperbola that are parameterizable by an angle form a group that is equal to a subgroup of the point addition on a hyperbola. So yeah, I know we went through quite a bit today. Did I send you the recording of the last session? Let's check.
I don't think I got it. Nothing check. Yeah, I haven't gotten anything.
Okay. All right. I will make sure to send both of these videos because we went over a lot of stuff. I'll take any final questions. And so what I foresee right now is that I still owe you guys a proof of the associativity of this group, which is a very difficult part relative to everything else that we've done. And then we're just going to begin the section on trig identities. Unless you want me to prove anything else is, I guess, what I was needed to end with there.
I'm good with your plan.
All right. Any questions about this stuff? Any comments?
Not really.
Well, let me just say this is like a rare example. You're not going to find this example of a group or an equivalence of groups in just any abstract algebra textbook or any geometry textbook or any elliptic curves textbook. I don't know. This is a good thing to know that not enough people know. So yeah, enjoy the rest of your Wednesday, I guess. If you have anything that's not related to this you wanted to talk about, then I'll stick around. But otherwise, you're free to go.
Jarrett, bye. Thank you.
Later, Ashith.
Hi. I'm just wondering. So in Taiwan, I think they use like AMC results for some kind of college placement. Does the US do the same thing or similar thing?
Well, every college application that I've looked at hasn't asked for those kinds of things, but maybe if you're applying to like a really prestigious school for a math degree, they would ask for it. But I would be surprised if they factored it in, especially outside of just the usual, is this a very particularly exceptional applicant, I guess.
Okay.
Yeah.
All right. Thank you.
Later.
Later.